I just attended the APS March meeting in Portland, Oregon, where over 7,500 condensed matter physicists presented on their current research. A surprising number of the presentations covered a vast array of different energy capture and storage technologies, and inorganic photovoltaics, or IPVs, were focused on during many sessions. The Department of Energy has a renewed interest and thus increased funding for renewable energy technologies that significantly impact solar technologies. 3 energy innovation hubs were created to stimulate research in clean energy, one of which is the Fuels for Sunlight Hub, which received $25 million in 2010 and will have similar funding in 2011. This program supports research intended to increase the efficiency of solar energy production and thus directly supports research of photovoltaic solar cells. Photovoltaics have primarily been based on the silicon p-n junction, which has a theoretical upper limit on efficiency of roughly 30%. Thus, no matter how cheap silicon solar cells become, they will never convert more than 30% of the incident sunlight into useful energy. This raises the question of how to improve efficiency. This is a graph of the solar spectrum. As you can see, a silicon p-n junction absorbs photons from a very small portion of the solar spectrum. Thus, in order to improve the efficiency of solar cells past that of single junction silicon, future cells must incorporate a larger portion of the spectrum. The blue curve corresponds to the highest efficiency silicon cells, which max out near 28%, while the purple curve shows multi-junction cells, which have shown efficiencies exceeding 40%. Thus, multi-junction cells are already over 40% more efficient than silicon. Multi-junction solar cells combine more than one single junction cell, stacked on top of each other so that the overall photovoltaic can utilize a wide range of the solar spectrum. The current favorite amongst condensed matter physicists is indium gallium nitride, which can cover most of the solar spectrum. It also has energy bands which match up well with silicon, which increases the efficiency even further. Another promising type of solar cell is an intermediate band solar cell, which is a single junction cell that has an energy band in between the valence and conduction bands. This allows for a wider range of photon absorption than a single band, without the complications of creating a complex heterostructure as is necessary for a multi-junction photovoltaic. The Department of Energy is making solar cells a priority, and thus it is the researchers' responsibility to provide alternatives to the single-junction solar cells of the past. Multi-junction cells, as well as intermediate band solar cells, have the potential to absorb photons from a much wider range of the solar spectrum, and thus are good candidates for the future of solar cells. However, with the added possibilities introduced by complex structures comes an increasing number of issues to resolve, such as the nature of the interfaces between multi-junction cells, as well as the complex band structures of intermediate band solar cells. Increased efficiency brings along a new plethora of opportunities, but it also brings many intricate problems that need to be addressed.